All right, so now we're going to cover the A to D converter, and also one option for triggering the A to D is from other peripherals. It comes across from other peripherals. So we have a cross triggering unit which will be able to trigger special A to D conversions. So this is just a quick summary. We have actually 10-bit and 12-bit A to D on the 5607B. We've got a number of channels, and you probably don't need all these channels. But if you do need them and you need more, we can add an additional external multiplexer, analog multiplexer, which we won't go over because I don't think it's necessary here. Accuracy is a couple bits internally. If you had a multiplexer, it would be 3 bits. It takes about a microsecond to convert a channel. That's the fastest. You can do it slower. Range, 0 to 5 volts. Everyone got that? 0 to 5 volt input. And we've got all these channels. And in other words, we have all these analog input pins. And every input pin or channel, after you do a conversion, has its own unique data result register. It's dedicated to that. So if you have 50 A to D pins, you will have 50 result registers. We don't have 50 here, obviously, but you get the idea. The signals for the pinouts are named such. We have a 12-bit A to D, our precise A to D, with ANP for precise, analog input for precise, channels 0 to 15. Then we have our standard 10-bit A to D, which has 0 through 7 and 8 to 27. And when you want to convert a channel with the A to D converter, you have to select a channel according to its number. And the precise is 0 to 15, but the standard channel 0 is channel 32. Okay? And when we get to the special trigger from the cross-triggering unit, you have to know the same thing applies. Okay, so this is probably the key slide. How does it work? Well, we have 3 triggering modes: normal, injected, and cross-trigger. And most of the time, for everyday stuff, you'll just use a normal mode. And when you start it, it can just do one scan, one shot, or it can continuously scan. And it will continuously do conversions on the channels that you select. And how do you select the channels? There's a normal conversion mask register, and this is 32 bits. And each bit corresponds to one of these inputs here. So actually there are 2 registers. There's more than one here. And so you select a channel by setting a bit in the normal conversion mask register. And you start this normal scan by just setting the end start bit. And this is what's in the example in the cookbook app note, is we set a few channels here to do conversions, and we just tell it to go. And it goes forever. It's funny, one of the customers said, I asked him how he's using it. Well, we don't do that injective stuff or cross-trigger. We don't need that. We just have these 12 channels, and we just set it to normally scan, and we just scan forever. I said, what, you mean you just keep going all the time? And he said, yeah, what's going to happen? Is the A to D going to get tired? But that's a very legitimate way to do it. You just keep continuously scan and convert. And then your software always reads the latest value. But you may want some synchronization to that, and that's up to you. But maybe every once in a while, you're going to have an interrupt. And that interrupt might say, hey, right now, forget what you're doing with the A to D. I want you to convert these channels, 5, 10, and 12, right now. So we can have an injected mode here, option, where we will specify channels 5, 10, and 12 in this injected conversion mask register set. And then they will take priority. They will preempt a normal scan conversion. So whatever was being scanned before is preempted and is just suspended, And then when these complete, then it resumes where it was. And to trigger an injected conversion, we either set this bit or PIT 2 can be configured to trigger it. And here's how that works over here. Okay, so there's a third way to preempt, and this is the highest preemption. This always takes precedence over whatever else is going on. That's a cross-triggering unit. And this is generating a trigger to a single channel. This is just one A to D input. And you can have this trigger occur from a different PIT, like PIT 3 or PIT 7, or a whole bunch of eMeos channels. So an eMeos channel like a PWM expires, or timer expires in eMeos, or an input, whatever it is, then you can trigger a single conversion. Now, be careful though. If two of these trigger occurs at once, only the first one is recognized, second one is lost. If an injected and a cross trigger occurs at the same time, only cross trigger works. The others are lost. So you have to work on scheduling if you care. So these are the analog channel inputs, and just a little graphic here. These are the data registers that line up with those. Two more things. One is watchdog. And basically, you can set an upper threshold and a lower threshold. And or we've got pairs of these thresholds, 4 to 6, depending on which chip you're using. And we can have an interrupt occur when one or more of these thresholds is exceeded. So we can now use that as a trigger. Everything's fine, everything's fine. Ooh, I got to tell the CPU I'm outside this boundary. That can be very useful, saves a lot of processing power, right? That's the way we try and get more throughput in these devices. This is just an example. Make the peripherals smarter. So you select the channels to be converted for either normal or injected. So there's normal registers and injected conversion mask registers. And then the results show up in that channel's data register, which also has a bit to indicate, hey, there's valid data here or not. And if you don't read it and another conversion takes place, then there's a bit to tell you that you were overridden. You know, you never read the last one. If you care, you know, it was overwritten and is lost. And then also there's a result here to tell you the type. Was it a normal conversion or an injected, you know, trigger conversion, or from the cross-triggering unit? We can also do interrupts at the end of a normal conversion, like a whole bunch, or a specific channel, or one or more channels complete. Same thing for injected, the whole injected chain, or a specific channel in that chain, or a cross trigger. So, and the analog watchdog threshold. So we have all these different interrupt options. The only other thing is that this cross-triggering unit, and once again, this is, you can get a trigger for the A to D all the way across from the eMeos or the PIT. And we will need to set up what we call event registers in there, and it's straightforward how to do that. There's an example in the book how to do that, so I won't go into it. But I do want to cover what the cross-triggering unit can do for you, especially for the eMeos. The eMeos has this PWM-T mode where we can set up a PWM, you know, to drive, for example, a solenoid. You drive it during this period, and you know, you get a lot of overshoot initially, so we can have a third count that is specified to trigger an A to D conversion. Because this is what we have. We have this overshoot, and this is really when we want to do the current measurement right here. Or here's another one right here. Not here, not here. So this new eMeos mode allows us to do that, and we can sample it. Now let me just describe what the cookbook will do before we get into eDMA. And let me just go back here to the beginning. there's an ADC with software trigger, continuous scan, and so basically we're going to sample channels, the standard channels ANS 0, 1, and 2. And these are on port pins B8, B9, B10. The code is pretty short. We init our modes and clock. Look at this. We initialize the pads for analog, and there's 4 registers we write to start it. We initialize it for scan mode. We select the channels. We have conversion times set for, and this is just a table out of the manual, for 32 megahertz ADC clock. And we say start, and now they're converting. And I just wait for a flag that says, hey, I'm complete. I wait for the first, for the last scan to complete in the chain. And now I can read the data, result 0, 1, 2, and I convert them to millivolts because it's just easier to read. And so we can hook up on the board different ones. So in the on the board, when we convert this, if you'll notice there's a little blue pot here. And this pot is connected to a different channel than the 3 I connect to. So one exercise is for you first just to run the program, and you'll read about 1.6 millivolts, or 1.6 volts, I'm sorry, because they're floating. And you have 2 options. You can take a jumper wire, which we will give you as a graduation present, because we don't have any jumper wires with board. But yeah, we need some jumper wires for this. And you can connect the port pin, which is port C or whatever it is for the analog, over to the pot. Then you can play with a pot, or you can connect the port pin to a ground on here or 5 volts and read that. But you need just to jumper the wire. And in the reference manual for the eval board, and you all have this on your CD because I printed it out from it, in there you will have where these pins are located on the board, and there's the last page has a little diagram, and I just took this to write up where I find things. But all the information is in here as to where these port pins are located, and you can find ground on the board. But you need some jumper wires, which were not included in the kit. We included the jumper plugs, but not the wires. So I'll make sure everyone gets a couple before we leave.